Welcome to the sixth lecture of Module 6. This is the last lecture in Module 6. It's entitled The Simple Harmonic Oscillator in Three Dimensions, Solving Quantum in Higher Dimensions. So we're going to start by looking at the Hamiltonian for the simple harmonic oscillator in three dimensions. And it involves the sum of the Hamiltonians in each of the different dimensions. So I have a kinetic energy that is a px squared over 2m plus a py squared over 2m plus a pz squared over 2m. And then I have the potential energy terms, 1/2 m omega x squared rx squared plus 1/2 m omega y squared ry squared plus 1/2 m omega z squared rz squared. And you can see if I just match up the x pieces of that Hamiltonian and the y pieces of that Hamiltonian and the z pieces of that Hamiltonian, I have three different one-dimensional Hamiltonians that I have added together. I also want to note that we have looked at the general case here where we put a different frequency in each of the different directions. So the frequency or the spring constant in the x direction need not be the same as the spring constant in the y direction, nor in the z direction. So there's a simplification that will arise because this is the sum of the one-dimensional Hamiltonians in each direction. Let's first recall the canonical commutation relation. That says that Ri commutator with Pj is equal to IH bar delta Ij. Note that when I does not equal j, I get a commutator. So the x position operator commutes with the y momentum operator and so forth. It's only when they're in the same direction and I have a position and momentum operator that I get a non-zero commutator. And that commutator of the position with momentum in each of those directions is just given by the IH bar, the standard canonical commutation relation. So the operators in the different spatial dimensions commute. That means each of those one-dimensional Hamiltonians commute with each other. So how do we find the eigenvalues and the eigenvectors? Basically, we use what we know. It's going to be the same thing as what we did before. And in fact, most of what we're going to do in this lecture is simply applying things that we have already done. And so it just requires you to have a good mastery of the things that we've already done and keep an open eye out for how we apply it in different contexts. All right, how did we solve the one-dimensional problem? We introduced raising and lowering operators. So we're going to do the same thing here. We're going to define the ladder operators. A sub j is square root of m omega over 2 h bar r hat sub j plus I square root of 1 over 2 m omega h bar p hat sub j. Notice that I match x with x, y with y, and z with z in each of the three different lowering operators. I also have corresponding raising operators by just taking the Hermitian conjugate of this equation. And all that does is changes the sign in front of the I. Now, we know the commutation relation between these two different ladder operators. If they're in the same direction, that commutation relation is 1. If they're in different directions, it's 0 because all the operators commute when they're in different directions. So now our states are formed in what's called a tensor product, and I do want to carefully explain this. We have a tensor product of an energy state for the one-dimensional problem corresponding to the x direction, tensor product with the corresponding operator in the y direction and the corresponding operator in the z direction. And when we look at this ladder operator, so let's take, for example, a sub x, the ladder operator in the x direction. That can only act on the nx state. It doesn't act on the ny or on the nz state because those are in different spaces. And so we typically will write that operator as a tensor product as well. We would write it as a AI tensor product with the identity in the y direction, tensor product with the identity in the z direction, so that when we act that operator on a tensor product state, I have identity operators acting on ny and nz, and I have the ladder operator acting on nx because the lowering operator was in the x direction. And then we know exactly what happens for that from all the work that we've done with simple harmonic oscillator in this module. So let me just summarize that for you. So as an example, as a second example, we'll look at what happens with the ladder operator in the y direction. We would write that as identity tensor product AY tensor product identity. And as you can see, putting in all of these tensor products really gets cumbersome and annoying after a while. And so we're going to just drop the tensor product notation, but you have to keep in mind that the AY operator only acts on the y part of the wave function, and the AX only on the x part, and the AZ only on the z, and so forth. You have to keep that in mind when you're working in higher dimensions and you have these tensor products, because we really do want to suppress this tensor product notation. It simply gets to be too unwieldy to work with. All right, so after I've introduced those ladder operators, I can factorize the Hamiltonian. And here's the factorization. It's just the sum of the three factorizations for the different dimensions: h bar omega x a dagger x ax plus a half, h bar omega y a dagger y ay plus a half, and h bar omega z a dagger z az plus a half. That's all there is to it. Now, what about the tensor product state? Well, we're now going to use this compact notation where we put the nx, ny, and nz just in one bra. We'll do a similar thing in the kets. We often put commas between the numbers so that we can differentiate that they really are acting on the different states. And then, of course, we just read the energy off. When the a dagger x ax acts on this state, remember it only acts on the nx part. And it's going to give me nx because it's a number operator. So I'll get nx plus a half times h bar omega x. When the a dagger y ay acts, it's going to give me an ny. And when the a dagger z az acts, it's going to give me an nz. And so you can immediately find that the energy E of nx, ny, and nz is just h bar omega x nx plus a half, plus h bar omega y and y plus a half, plus h bar omega z and z plus a half. And the wave function itself factorizes as well. I'm going to take a tensor product of an Rx tensor with an Ry tensor with an Rz. I'm going to take the inner product of that with the energy eigenstate nx, ny, and nz, and that's what we call the wave function. And using the rules for tensor products, that factorizes into three separate inner products: Rx with nx, Ry with ny, and Rz with nz. And then we know what those are. Each of those are the one-dimensional wave functions. So I can write that psi nx of Rx, psi ny of Ry, and psi nz of Rz. Now let's carefully work through what this is for the ground state. So in the ground state, the energy of the ground state corresponds to nx equals ny equals nz equals 0. So the ground state energy is h bar omega x times a half plus h bar omega y times a half plus h bar omega z times a half. So now after I introduce the products of each of those different one-dimensional wave functions, I get the three normalization factors in front. That's an m omega x over pi h bar to the 1/4 power, and m omega y over pi h bar to the 1/4 power, and m omega z over pi h bar to the 1/4 power. And then I have the product of the three Gaussians, but because those are exponentials, I can move each of the exponents of the products into one single exponent. So I'll get e to the minus 1/2 m over h bar omega x rx squared plus omega y ry squared plus omega z rz squared. And then that's the wave function. And so it's that simple. We just put together the results from the one-dimensional problems, and we then get the three-dimensional results. All right, there's a very special case that we like to look at, and that's the isotropic three-dimensional simple harmonic oscillator. This is the case where we choose each of the frequencies to be the same. And now the Hamiltonian is h bar omega times the sum of these number operators plus 3/2. A dagger x ax plus a dagger y ay plus a dagger z az plus 3/2, a whole thing multiplied by h bar omega. Now, the energy then can be replaced by these numbers nx, ny, and nz, and I have to add the three of them together. And you can immediately recognize that in any case where the sum of that nx plus ny plus nz gives a particular value n, then all of those states will have the same energy. And when different states have the same energy, we call that degeneracy. And we're going to carefully go through what degeneracy looks like for the simple harmonic oscillator. So let's start by looking at the ground state. The ground state corresponds to each of those indices equal to 0. And so I just get h bar omega times 3/2. There's only one way I can have each of those three indices equal to 0, and that's to have all of them 0. So the degeneracy is just 1. Let's look at the first excited state. The energy is h bar omega times 5 halves, because I just have to add an integer of 1 plus the 3 halves. But there are three different ways I can do that. I can have 1, 0, 0, I can have 0, 1, 0, or I can have 0, 0, 1. So the degeneracy is 3. The next excited state will be h bar omega times 7 halves, because I have to add yet another integer into the energy eigenvalue. And now there are 6 ways I can do this. I have 2, 0, 0, 0, 2, 0, 0, 0, 2. I also have 1, 1, 0, 1, 0, 1, and 0, 1, 1. And all of those have the same energy, h bar omega times 7 halves. What you can see from this is that the degeneracy grows as the energy increases, and it actually is pretty difficult to determine the degeneracy for any given energy, especially a large one, except by just directly enumerating all possible ways to do this. And the mathematical term for this is finding the partitions that sum to the particular integer n that corresponds to the energy En equals h bar omega quantity n plus 3 halves, which is what each of the different energy levels are. That's a well-known, very hard problem. If any of you saw the biography movie on Ramanujan called The Man Who Loved Infinity, you would have seen in that movie there was a large discussion about the question about how you solve the partitions of different integers, because that was one of the problems that Ramanujan worked on. Now, the wave functions are also can be isotropic, but they don't always have to be isotropic. So I want to carefully go through this. Now, the Hamiltonian is spherically symmetric. If all of those frequencies are the same, the potential energy becomes 1/2 m omega squared rx squared plus ry squared plus rz squared, which is 1/2 m omega squared r squared. And that doesn't matter. That is the same regardless of how I rotate my coordinate system, because I'm just working on the surface of a sphere. And so we expect that some of our wave functions will be functions just of r squared. It's easy to see that the ground state will be that way, because if omega x equals omega y equals omega z, if you remember back to that slide, we would factor out that omega and we'd be left with an rx squared plus ry squared plus rz squared. So that's just a function of r squared. But in general, not every function is this way, and we have to actually work hard to get a function by looking at linear combinations of degenerate energy eigenstates to get it into that form. And I'm going to show you how we do this in one particular case. It's the case where the energy is equal to 11 halves h bar omega. And we're going to do that by choosing the right linear superposition. So this calculation requires a fair amount of bookkeeping. There's nothing complicated about it, but it's very easy to make a mistake. And so let's look at how we do this. The wave function, we're going to only worry about even powers of the Cartesian coordinates. So we're not going to look at all possible energy eigenstates that have energy h bar omega times 11 halves. We're only going to look at these 6. 4, 0, 0, 0, 4, 0, 0, 0, 4, 2, 2, 0, 2, 0, 2, and 0, 2, 2. Now, remember how we form those wave functions. The ground state, which is the case where there's a 0, that just has the normalization factor times e to the minus 1/2 m omega over h bar rx squared. A psi 2 has that same factor and the same Gaussian term, but it also has a 1 over square root of 2. Remember, there's a 1 over square root of n factorial for psi n. And it has this Hermite polynomial of the square root of m omega over h bar rx. And then the psi 4, which is the other wave function that we're going to have in these different combinations of wave functions, that has a 1 over square root of 24 because 4 factorial is 24, and it has the h4, and everything else is the same. Okay? And let me just remind you what those Hermite polynomials are. The h2 is 4z squared minus 2, and the h4 is 16z to the 4th minus 48z squared plus 12. Okay? We're going to calculate the different linear combinations that give us terms that are proportional to, that have functions that depend only on r squared. Okay, let's go. So we're going to drop the common factors. Those were the normalization factor and the Gaussian factor. And we're going to form combinations that are combinations of r to the fourth, which is rx squared plus ry squared plus rz squared squared. And that's rx to the fourth plus ry to the fourth plus rz to the fourth plus the cross terms, which are each weighted by factors of 2. And what we need to do is get the right weighting coefficients. And so psi 400 plus psi 040 plus psi 004, that's going to involve H4s, and it's going to involve H4s of Rx, of Ry, and of Rz. I have suppressed the square root of m omega over h bar terms. We actually have to put those back in, so you can think of these as schematic calculations at this stage. Adding them in just made things just too long and complicated in the formulas. But I am doing a little bit of a cheat by not putting those formulas in. It's very easy to correct for them and get them in there properly. Okay, so I'm going to have the H4 for an Rx, that's the 400. I'm going to have the H4 for an Ry, that's the 040. And I'm going to have an H4 for the Rz, that's the 004, and I'm going to add them all together. So you see I'm going to get a 16 Rx to the fourth plus a 16 Ry to the fourth plus a 16 Rz to the fourth. I'm going to actually write that as r to the fourth and then subtract off those cross terms. So that's 16r to the fourth minus 32 rx squared ry squared plus 32 ry squared rz squared plus 32 rz squared rx squared. That is just adding the 16 z to the fourth terms for the x, y, and z components. And then I have minus 48r squared. You see, that's going to have a term that will be an rx squared plus an ry squared plus an rz squared. That actually just gives me the net of an r squared, so I get minus 48r squared. And then I have the plus 12, but I have a plus 12 for the x direction, for the y direction, and for the z direction. So that gives me a plus 36 when I add them all together. Now, when we look at the 220 terms, I get and there's the 1 over square root of 24, that's the 1 over 4 factorial in the upper result that we get from the 1 over 4 factorial. Now, for the 220s, 202 and 022 terms, I have two H2s. Each H2 has a 1 over square root of 2, so the net is a 1 over 2 prefactor. And then I have to look at a product of a 4 Rx squared minus 2 times a 4 Ry squared minus 2, plus the same thing with a Ry squared and an Rz squared, plus the same thing with an Rz squared and an Rx squared. So each of those products, when we add them together, you should be able to convince yourself that we'll get a 16 Rx squared Ry squared plus 16 Ry squared Rz squared plus 16 Rz squared Rx squared. We will also have a factor of 4 times a minus 2, that's a minus 8, and then the cross terms will be Rx squared plus Ry squared, there'll be Ry squared plus Rz squared, and there'll be Rz squared plus Rx squared. And when we add those all together, you see that's a 2r squared that we get by adding all of them together. So the net is a minus 16r squared. And then I have the factors of 4 for each of these different terms. There are 3 of them, so they add together and give me 12. So if you had any trouble following this, I do recommend that you pause the video and carefully work through what these different wave functions are. And remember that we dropped these square root of m omega over h bar terms just so that we could have some simplicity with what we were working with. If you want to work it out, including those factors, go right ahead. You can do that. All right, we have to find the right linear combination of these to get rid of the cross terms. So first you have to note that psi 400 plus psi 040 plus psi 004, that's the expression we got before, the same with the psi 220s, etc. terms. Now, if I multiply the psi 220 terms by 2 over square root of 6, and I bring the 1/2, I write 1 over square root of 24 as 1 over 2 root 6, and I bring that 1/2 in, you see I'm going to get 1 over root 6 times 8r to the fourth. I'm going to get minus 24r squared minus 16r squared. That's minus 40r squared. I'm going to get plus 18 plus 12. That's going to be plus 40. And you see I have minus 16 times this cross product squared, but I have a plus 16 from the other term. So those cross product squared terms are going to cancel. And I'm now left with a function that's just a function of r squared. And so by looking at the right linear combinations of these terms, we can indeed find the combination that will give us the correct result that is equal to a function of just r squared. But note that any of the other linear combinations will not be just functions of r squared. So what we learn is that while some of the wave functions can have the full symmetry of the Hamiltonian, most of the wave functions are not isotropic. And so this is a very important result. Not all wave functions have the same symmetry of the Hamiltonian. And this is something that we're going to see happen again and again in different calculations that we work with in systems that have degeneracy. All right, there's one last thing I want to cover. That's uncertainty. Uncertainty adds in quadrature when we have higher dimensions. What do I mean by that? Well, if I calculate the delta squared of r for nx, ny, and nz, it actually is just the sum of the delta squareds for each of the different spatial directions. You can arrive at this conclusion by remembering that it is ex over omega x plus ey over omega y plus ez over omega z, and then I just add them together. Or you can recognize that, look, r squared is actually del squared of x plus del squared of y plus del squared of z, and each of those del squareds, they factorize because of the factorized form of the wave function and so forth. However you want to look at it, there are many different ways. Please convince yourself that uncertainty adds in quadrature in this fashion. And that's true for position as well as for momentum. Now, what happens when we look at the uncertainty product? Well, I have to take the square roots, and I look at the product of those square roots, and I find that it's equal to h bar over 2 times 2nx plus 2ny plus 2nz plus 3. And when I look at the ground state, you see that the uncertainty now has a 3/2 h bar omega. And so it's bigger than what we had in one dimension. It's in fact 3 times bigger for the uncertainty product. Okay, that's all that we have for Lecture 6 of Module 6. We covered the simple harmonic oscillator in 3 dimensions. We're going to look at applications of the harmonic oscillator to different quantum phenomena and different quantum systems during the class time. And with that, we're going to end the lecture.